Module 5, Objective 5, describe the changes that occur in the generation and propagation of an action potential. Action potentials are nervous impulses or electrical signals that are propagated along the cell membrane, particularly down the axon. So they're propagated changes in the membrane potential that affect the entire excitable membrane, beginning at the initial segment of the axon, moving down to the axon terminal. Action potentials do not diminish as they move away from the source, and they're stimulated or created by a graded potential that is strong enough to reach threshold. Threshold for an axon is approximately a 10 to 15 millivolt change. So that would put it at negative 60 to negative 55. If you were to consider our time scale, here's negative 90, negative 70, 0, and 30 millivolts. Rest is identified at negative 70, and a graded potential, if it's strong enough, and by strong I mean 10 to 15 millivolts. So if you go from negative 70 to negative 60 or negative 55, you reach this sort of magical line that we call threshold. And if the graded potential is strong enough to reach threshold, that graded potential will be converted to an action potential. So each neuron is going to receive information in the form of graded potentials on its dendrites. So these dendrites are all getting graded potentials, okay? And those graded potentials are going to add up. And if they add up to threshold, then you're going to get the initiation of an action potential. So here we are at rest. We've seen this image before. Ion channels are closed. Sodium is localized outside of the cell, while potassium is largely localized inside of the cell. Step 1, you get a depolarization to threshold. So if a graded potential is strong enough to reach that threshold, that negative 60 to negative 55 millivolt transmembrane potential, then you get the activation of an action potential. So step 2, activation of sodium ion channels and the rapid depolarization. As soon as these ion channels open, you're going to get an influx of sodium ions driven by, again, the chemical gradient and the electrical gradient. And as sodium floods in, you depolarize that cell membrane. And you can see here we're even depolarized all the way up to positive 10 millivolts. Action potentials exhibit an all or none principle. Any stimulus that is strong enough to create a graded potential that reaches threshold, then you get an action potential. And all action potentials are the same, no matter how large that stimulus is. So for example, if we look at our scale again, negative 90, negative 70, 0, and positive 30, we know that that threshold sits at somewhere right around here, negative 60 to negative 55. And if your graded potential is strong enough to reach threshold, it gets converted to an action potential. And what the all or none principle states is that it doesn't matter what this graded potential is. It could just barely reach threshold, or it could be very strong. The resulting action potential is going to be the same. So an action potential is either triggered or it's not. And again, if that graded potential reaches threshold, it is going to be triggered. Generations of an action potential. Step 1, depolarization to threshold. So a graded potential depolarizing the cell to threshold. 2, you get the activation of the voltage-gated sodium channels. So here we have a different type of channel. Now we're talking voltage-gated channels. So they open in response to some voltage, some change in the voltage. So once the activation of the voltage-gated sodium channels open those channels, sodium is going to rush into the cytosol. The inner membrane changes from negative 70 from rest to a positive number, and that results in a rapid depolarization. And we can see that here. So step 1, depolarization to threshold. These some stimulus that initiates an action potential starts with a graded depolarization that is large enough to open the voltage-gated sodium channels. The opening of these channels occur at the membrane potential known as the threshold. Step 2, activation of sodium ion channels and rapid depolarization. When the sodium channel activation gates open, the plasma membrane becomes much more permeable to sodium because sodium now can freely flow into the cell. The large electrical chemical gradient is going to drive the influx of sodium ions, so they're going to rush into the cytosol, and that's going to lead to a rapid depolarization. The inner membrane surface now has more positive ions than negative, and the membrane potential has changed from negative 60 to a positive value, and here we have just a positive 10. So all that influx of sodium, what's driving movement of sodium? You have the chemical gradient. Sodium wants to reach a state of equilibrium. You also have an electrical gradient. Sodium wants in because it was negative inside. But now, so many sodium had flooded in that it's no longer negative. Now it's positive 10 millivolts in this example. Step 3, the generation of action potentials. Inactivation of sodium channels and the activation of potassium channels at about positive 30. When your transmembrane potential of your cell reaches positive 30, sodium channels close and your voltage-gated potassium channels now open. And potassium is going to flood out of the cytosol. So if we have our scale, negative 90, negative 70, 0, plus 30. We start off at rest at negative 70. We get a graded depolarization. If that's strong enough to reach threshold, we get a rapid depolarization. At about positive 30, voltage-gated sodium channels close, voltage-gated potassium channels open. Now, potassium is going to flood out of the cell. Why? 2 reasons. 1, potassium wants to reach a state of equilibrium with itself, so there is a chemical gradient pushing sodium out. Secondly, I keep saying sodium, but I mean potassium, so I'm sorry if I confuse. Potassium has a positive charge, and what is the charge of the transmembrane potential? It is now positive 30. Like charges repel, so potassium is going to be further driven out via an electrical gradient, and that triggers repolarization. As potassium floods out, we're going to go from positive 30 to a more negative number, and that is repolarization. Here we see that happening at positive 30. Your sodium ion channels close, your potassium open. Potassium is going to flood out because it wants to A, reach a state of equilibrium, which is the chemical gradient, but B, electrically, it is positive. It is now positive inside. It wants out. It's being repelled by the positive charge. So potassium is going to flood out. And as potassium floods out, this transmembrane potential is going to repolarize. It's going to move back down towards a negative number. Step 4, return to resting membrane potential. Voltage-gated channels begin to close as the cell reaches that negative 70 millivolt. So when the transmembrane potential reaches around negative 70, the potassium channels begin to close. As the potassium channel closes, it is a slow close. It is like a slow door. And as the door is shutting, more potassium leaks out, and that's going to cause a hyperpolarization. You're going to move beyond negative 70 to negative 90. And at about negative 90, that door has shut, so that that voltage-gated potassium channel is going to close. So after all the voltage-gated potassium channels close, the resting membrane potential becomes restored due to the sodium-potassium exchange pump. At that point, your action potential is over. So here we have step 4, the voltage-gated sodium channels are inactive, and the potassium channels start to close at about negative 70. And as this door slowly swings closed, more potassium channels, ions rather, flood out, and that leads to a hyperpolarized state. Once all of the potassium-gated channels close, sodium's closed, this cell membrane can return to rest, and that's facilitated by the sodium-potassium exchange pump, which is going to kick sodium out of the cell while exchanging it for potassium. And that's going to get us back to negative 70, which is our resting potential. The refractory period, from the beginning of an action potential to the return to rest, that is the refractory period. During the refractory period, the membrane will not respond to the normal stimuli that started the process. So refractory period is a time period in which the membrane is not going to respond to a second round of stimuli. We can divide the refractory period into two. We have the absolute refractory period. The absolute is defined by having all the voltage-gated sodium channels open or inactivated, and the membrane absolutely cannot respond to a further stimulation. There is the relative refractory period. This begins when the sodium channels regain their rest, the resting condition, and it continues until the membrane stabilizes back at rest. And during relative refractory period, only a really strong stimulus can initiate another round of action potentials. So let's sort of look at this whole process in a different format. We recognize the scale here on the y-axis. We have, I'll add negative 90 here. Negative 90, 60, 0, and then positive 30. And we start with the resting membrane potential right here in blue. Now it's black, and that's sitting at negative 70 millivolts. And the first thing we experience is a graded potential. Remember, this is a temporary, localized change in the transmembrane potential. If the graded potential is strong enough to reach threshold, as identified by negative 60 here, it gets converted to an action potential, and a rapid influx of sodium ions lead to this rapid depolarization of the membrane. All of that, from threshold up to the positive 30 we see here at step 3, this starts absolute refractory period. Remember, absolutely under no circumstances can a second action potential be initiated. Once we have reached positive 30, we know what happens up here. The sodium channels close, the voltage-gated potassium channels open, and potassium starts to flood out of the cell. As potassium floods out, we get a state of repolarization, and repolarization is going to continue until we move out of the absolute refractory period here in red and enter into the relative refractory period. Remember, during the relative refractory period, the membrane can respond if the stimulus is larger than normal. So, relative refractory period. As the cell continues to repolarize, it's going to continue to move down at about negative 70. Something special happens there. The voltage-gated potassium channels start to close, but that door is really slow at closing, so more and more potassium leak out, and you get to a hyperpolarized state down to about negative 90. Once the potassium channels close, then the cell will revert to rest through the sodium-potassium exchange pumps. So the absolute refractory, absolutely no way can a second action potential be generated. Relative, it could happen if the stimulus was great. So depolarization results from an influx of sodium, while repolarization involves the loss of potassium ions. The sodium-potassium exchange pump is going to return the concentrations of the pre-stimulation levels, with sodium localized outside of the cell and potassium localized inside of the cell. It's also going to maintain the concentration gradients over time. This is an active process, so ATP, the sodium-potassium exchange pump utilizes ATP in order to exchange 2 potassium for 3 sodium.